introduce Professor Michael Yampolsky, Misha Yampolsky from the University of Toronto. If someone doesn't know Misha, let me just spend a second. I mean, he studied, he graduated as an undergraduate at the State University of Kharkov in Ukraine, and he got PhD at Stony Brook. And he has had positions in Yale and EHS, and then he landed as a professor at the University of Toronto, where he established the research group in dynamical system. So Misha is the father of the dynamical system group in Toronto, which has a lot of distinguished colleagues, some of them former students of the Scuola Normale in Pisa. He has written more than 70 papers and many books, including books on mathematical methods of life sciences, theory of computation and dynamical systems. And so he is, of course, an expert of dynamical systems, both complex and real, and renormalization techniques. He's the director of the newly established Institute for Nonlinear Sciences.
Nonlinear analysis.
Nonlinear analysis at the University of Toronto, which has an agreement, the collaboration with the Scuola Normale. And I'm extremely happy that he is visiting us still for just a few days. But I mean, and Misha will give a talk on renormalization, from renormalization of diffeors to critical circle maps and Herman rings for two-dimensional maps. Okay, thank you very much.
Stefano, thank you very much. This is a very nice introduction. Okay, so I'm going to talk about renormalization in dynamics. Can I actually see a quick show of hands? How many of, I mean, I just want to see which of you are familiar with the concept of renormalization in dynamics. Okay, so I'm going to, no worries. I mean, for those who are not, you're not going to understand anything. No. It's not going to be like this. I'm going to give you a very general definition. So here is a general definition. And really, the way these things go, this definition is going to be too general. So it's going to be, you know, almost but not entirely useless. So it goes somehow like this. We have a dynamical system. So we have some map on some space from some space X to itself. Maybe finite dimensional, maybe a subset of a Ren. And then we take a proper subset. So there's Y, which is a proper subset of X. And we'll look for what's known as the first return map of Y. That is, we take a point Y in the set Y, and we iterate it until it comes back, right? So, so n of Y will be the, you know, will be a natural number that is the smallest such that this iterate of Y is back in this set. Of course, it might be infinite. I mean, the point might never return. But in this way, we get what's known as a first return map. Of Y, which maybe I'll denote as capital F sub Y. And this is from a subset of Y back to Y. Right? So which is just F n of Y of Y. And then comes the interesting part. So the next step is to recover from this dynamical system, which acts on the big space X again. So we define some sort of a rescaling or renormalization. So A, which maps Y to X, is, you know, a rescaling, or you could call it renormalization right? And then we define, well, I happily ran out of room, so maybe I'll write it here. And then we define renormalization of f. Maybe I'll denote by script r, is A inverse capital F YA. So in other words, this is again a map from X to X, so at least from a subset of X to X. So this is a general scheme. So renormalization, in other words, is a rescaled first return map. All right, so the study of renormalization of dynamical systems is very important. Otherwise, I wouldn't be talking about it. But what is it? What are these things good for? Why does one to look at such a procedure? So generally, there are two general directions in which results go. Okay, so one of them. Okay, so this is some sort of a transformation on the space of dynamical systems from X to X, right? So you start with a map F and you get a new map, which is this script R of F. So one of the things to notice is that sort of by definition, the geometric aspect of this is that the orbits of this new dynamical system, so some sorts of rescaling zooms in into the orbit of the original F, right? Because we're taking an iterate, which of course preserves the orbit as a set, and then we rescale, so somehow enlarge. So one observation is that if after such sequence of rescalings, the maps themselves get closer, that means that the orbits somehow on a small scale look more or less the same. So, and the general idea is that properly measured, so if you get something like this in some, properly defined norm, then this has the effect of what's known as geometric rigidity, which usually expresses itself through saying something like F is smoothly conjugate to G, where smoothly should be understood, also in an appropriate sense, appropriately smoothly. So these sorts of results are known as geometric rigidity. And the idea is, again, that if you renormalize and the maps get closer, that means the orbits on a small scale look the same. So you could somehow change coordinates to replace orbits of one map with the orbits of the other, and this change of coordinates would be nice. Another upshot of the construction, and this is more delicate and somehow could be more rewarding in some way, is that you could try, R is a dynamical system on the space of dynamical systems. It's an operator acting on the space of maps from X to X. And you could try to understand the dynamics of R as such. So you could study this as a dynamical system on the space of maps. And then you could get some interesting results because the dynamics of R somehow, it could be quite different from the dynamics of F that you started with and quite informative to look at. So the other direction, let me just kind of broadly say, so this would be the study of the dynamics of R on the space of maps. Okay, so like I said, this is way too general to be useful. So let me give you a very specific example. Let me talk about the situation when x is one-dimensional, when it's a circle. And I'll be talking about renormalization of homeomorphisms of the circle. Okay, so first, a little bit of the basics. So I'm going from something that's really, really general to something that's extremely specific. Okay, so okay, so let's, to fix the ideas, let me denote by T the affine manifold R mod Z, which is, of course, isomorphic to S1 by the exponential map. So this is a circle, and I'm going to look at homeomorphisms of the circle. So F from T to T would be an orientation preserving homeomorphism. Okay, so let's follow the recipe, which I just helpfully erased. So I have to define, I have to pick a subset of the circle. I have to define a first return map, and then I have to rescale it to get the circle back, right? So let's see where this leads us. So first of all, what subset of the circle should I pick? That somehow this is largely irrelevant to the theory as long as this is done in a consistent fashion. So in the same way for all maps. So here is how it's normally done. So let me remind you that the rotation number of F is the average angle by which F rotates the circle. And this is the limit as n goes to infinity. F bar iterated n times of x over n mod z. Where F bar is a lift of F to the real line. X is any point on the circle, and nothing depends on either the choice of X or the lift. You're going to get the same number. This is the average angle, right? If you take an actual rotation by angle alpha, then the rotation number is, of course, alpha. And for F, this is the average angle of rotation. Okay, so this definition goes back to Poincaré, and there are all sorts of basic properties, which I'm sure all of you have seen. So really the one thing that I would like to point out that you could actually read off the rotation number from the dynamics of F itself. For instance, in the following way. So let's take a representative of this in 0, 1. Let's expand it into an infinite continued fraction with positive terms. This is finite or infinite. I'm going to abbreviate this like so to save space. Now this is unique, so AI is a natural number. This is infinite and unique if and only if the number is irrational. For rational, there is an ambiguity in the last digit or the last 2 digits, but we won't worry about this too much. So, and of course, basic properties of continued fractions. These are used to get best rational approximations of ρ. So in particular, if you take the finite continued fraction convergent Pn over Qn, which is just the truncation of this continued fraction after n digits, I'm going to assume that there is at least n plus 1 digit in this thing, then these are best rational approximations of ρ. But also you could see Pn over Qn and the dynamics. If you take a point x on the circle, right, then Qnth iterate. Do you mind if I write an iterate as a power? I'm really not going to use powers very much in this talk. So this is the closest return, which means that there is no smaller iterate in between. And in fact, if you take the lift of the map, then to get to this particular point in the projection, you subtract Pn. Right? So that's somehow how you recover Pn over Qn. It's worthwhile to note that the returns given by Fqn and Fqn plus 1 occur on the opposite side. This is basically elementary. And but this is a useful way of connecting the dynamics here with the actual number rho, with the rho itself. Okay, very good. So how am I going to define renormalization? I'm going to do the following. And this is a choice that's almost the choice that's made historically. And again, it doesn't really matter what choice you make in the end, as long as you're consistent. So here's the choice I'm going to make. So I'll start with the point 0. Nothing special about 0, just I have to start somewhere. I'm going to take its first return, which is given by Fqn of 0. And then to define the nth renormalization, this is going to be the set Y. This is the subset of the circle to which I would like to consider the first return map. Okay. By the way, just keep in mind, F is a homeomorphism, right? So it's like a rotation. So Fqn is also a homeomorphism, so it's sort of like a rotation this way, right? And okay, so it's easy to see that the first return of this interval, of the yellow interval, is almost the iterate Fqn plus 1. I mean, almost, but not quite. Fqn plus 1 is closer to x, or at least, you know, it's supposed to be, but it sticks out a little bit the other way. So if I look at the interval Fqn plus 1, most of the yellow interval will return. But some of it will miss and will stick out. And right, this is the point Fqn plus 1 of 0. So here I need to give it a little extra kick to make it return. And it's easy to see that this little blue thing here returns under the iterate Fqn. Okay, so here this is the same point. This is Fqn plus Qn plus 1 of 0. This point here. Okay, so so the first return map of the yellow interval is a pair of maps, right? So on most of it, it's Fqn plus 1, but on a part of it here that will stick out, it's going to be Fqn plus 1 followed by Fqn. All right. Very good. So that's our first return map. Nice thing is that all points return, so that's wonderful. Now all that's left is to rescale this thing back to the circle. And I'll have my renormalization defined. Okay? And we're going to run into a problem here. Just honestly telling you, so you won't be upset with me. So we're going to run into a problem here. How do you glue an interval into a circle? Well, I mean, you have to glue the ends, right? So I have to pick a chart to identify a neighborhood of this point with the neighborhood of this point. And the chart is actually here. I mean, it's ready-made for me. It's FQN, right? I mean, this here is the image of this. So the blue map produces the gluon, and then this pair of maps gives you a well-defined map of the resultant circle, right? So I have to take this interval, 0, FQN of 0, enlarge it slightly, right? Quotient by x is equivalent to FQN of x. Maybe let's be precise. So I take some epsilon neighborhood of this, quotient by that, and that's a circle, right? Does everyone agree? Well, I mean, that's entirely untrue. The circle, I would like to remind you, is an affine manifold R mod Z, right? Your map F is a homeomorphism. Well, I mean, you could make it smooth. You can even make it analytic. But unless you start with an actual rotation, this map is not affine. So what you're getting here is not a circle. You're getting a one-dimensional manifold, which is topologically a circle. Maybe it's smoothly a circle if you have a smooth. Maybe it's analytically a circle, but it's not a circle. Okay? I mean, it's a really simple point that somehow led to a lot of interest and developments in the subject. So it's a conceptual problem. It's not just a small hiccup. So, okay. Well, I mean, so the scheme somehow fails because since I don't get a well-defined affine manifold here, I get not one map of the circle, but infinitely many. I mean, depending on which identification of the resultant quotient with the circle I pick. We'll get back to this in 5 minutes. But the first solution, the first historical solution, is not to glue. Okay, so don't look at maps of the circle. Enlarge your class. Look at pairs of interval maps. Okay, so without gluing. Then rescaling is very easy because you could just take, say, this interval and rescale it to the size 1. So your rescaling would just keep 0 at 0, send this point to 1. This would be, what did I call it? A, and then you could do a rescaling of the pair and you get renormalization. You could still view this as a poorly defined map of the circle. So in particular, it still has a rotation number, but it's no longer a circle map, right? So this procedure would define for you, so this is n, so this would be the nth renormalization of f, which is a pair of interval maps. I mean, if you want some technical jargon, it would be a nonlinear interval exchange transformation. With 2 intervals. Okay, so this is one way of doing it. And now for diffeomorphisms, I mean, for homeomorphisms, you cannot get very far, but if f is a diffeo, if f is smooth, even with finite smoothness, you can get quite a bit of mileage from this construction. So it's not difficult to show. I mean, it's completely classical. I don't know who observed it first. That if f is, you know, smooth, well, let's say C3. So if f is C3, then and the rotation number is irrational, so you could keep on doing this. But then renormalizations defined in this way converge to linear maps, in fact, exponentially fast. well, pairs of linear maps. So I'm going to write to the space of affine maps or affine interval exchange transformations, which is, of course, the same as the set of rotations. Because, I mean, if these two maps are affine, then you can glue this back into a circle and you get an rotation. It's worthwhile to point out that the rotation number of f the nth renormalization of f is the same as the rotation number of f, only translated to the left n times. Well, it's shifted to the left n times, so this is going to start with an plus 1, etc. Such a transformation is known as the Gauss map. It's analytic, so this is Gn applied, so raw, I'm sorry. Gn applied to rho of f, where the analytic formula for G is the fractional part of 1 over x. Right. Okay, so this is very good. So this tells you that, yes. Yes. So if I would like to define renormalization somehow in a coherent fashion, and my map only has finite smoothness or even infinite smoothness, right? It's best not to glue. I mean, it's a conceptual problem. We're not going to define our way out of it. Okay? But it's fine. I mean, this is a larger class. We'll look at nonlinear interval exchange transformations. They have to commute on a small neighborhood of the point where the domains intersect for this to make sense. But other than that, life is good, right? And you will have very nice convergence here. In fact, this is exponentially fast. I don't know, in some smooth metric and well, and at least C1. Okay. So, okay, very good. So now, if you remember my meta definition and sort of this general philosophy that I described, this should lead to some rigidity results, right? So we should start by saying that if f and g are closed, and their renormalization, if renormalizations of f and g are closed, in fact, in this case, if their orbits converge together exponentially fast, then we get a smooth conjugacy result. First of all, why on earth would something like this be true? So nice thing with explicit examples like this is that you can explain this also pretty explicitly. So I'm erasing this, and of course I'm going to regret it because I need this picture, so I'm going to put it back on. So if I start with some point, say 0, it doesn't really matter what point you start with, and you look at these returns fqn of 0, so then fqn plus 1 of 0 will be on this side. Let me denote these intervals something. So I had yellow here, and I had blue here. So let me call this in, and this then would be in plus 1. So that's the shorter arc of the circle between 0 fqn of 0 f. Really, to be precise, I mean, I don't know if they're actually shorter or not, but this is the yellow is the arc which doesn't contain fqn plus 1. So then it's a relatively easy exercise to show that if you iterate these intervals forward an appropriate number of times, you're going to get a partition of the circle. So union of, and you iterate them until they return to this picture. And I mean, we know how far we have to iterate the blue. So it returns here, and we know how far we have to iterate the yellow. The blue, you have to iterate fqn times, and then it comes back somewhere here. And yellow, you have to iterate fqn plus 1 times, and then it comes back here, right? So if I look at the union of fj, j goes from 0 to qn plus 1 minus 1 of in, union I goes from 0 to qn minus 1 of n plus 1. I'll call this en. This actually turns out to be a partition of the circle. So this is known as the nth dynamical partition of the circle. Now, renormalizations converge to affine maps geometrically fast. For them to stay close, well, for them to stay close, you need, I mean, on the affine maps, you just you just have the Gauss map. I mean, the affine maps are parameterized by the angle, by the rotation number. And on the rotation numbers, you have the Gauss map. This is crazily expanded, right? So, I mean, 1 over x is on the interval 0, 1 is a pretty expanded map. So for the iterative renormalizations to stay close, given that you converge to the affine maps, you have to have the same rotation number. And in fact, this is if and only if. So f rho f is equal to rho g, and it's irrational. I mean, this implies that the distance, again, say C1 between RNF and RNG goes to 0 exponentially fast. And now both F and G will have these partitions on each level. Right? The partition of the next level is just going to refine the partition on the previous one. The intervals in the partition shrink. I mean, the length shrink to 0 exponentially fast. Your map on a small scale is just like a rotation. And you could try to build a conjugacy between the maps just by taking appropriate intervals of the partition and identifying them, say linearly. So this would be a piecewise linear approximation of a conjugacy. And then you refine this. You go to the next level, you have some intervals in the partition here, and the corresponding ones here, and you do this again. And so on. And the question is whether this will converge. So for example, you could look at the situation when, so here's an example. Let's look at what's known as bounded type rotation number. So this is when the soup of AI and the continued fraction is finite. This translates into saying that there is a bound on how many intervals of the partition of the next level there'll be in the previous one. Okay, but then the geometry of the picture becomes the same exponentially fast, simply because, well, I mean, the number of pieces is finite, and each piece is exponentially close. Each piece here is exponentially close to the corresponding piece here, and there are finitely many of them. So they're all exponentially close. So from this, it's very easy to conclude that these approximate conjugacies converge to an actual conjugacy, which in this case would be C1. Okay. So this condition, by the way, is equivalent to saying that rho is the Fantin of order 2. For those who know what Diffenton numbers are. You could push this fairly far, but if your map's only smooth, then Diffenton conditions are the best you're going to get. And the best theorem in this vein is the theorem of Katznelson and Ornstein, which says that if rho f equal to rho g and is Diffenton of some order k, and f and g are in some CR, which is greater than k plus 1, then f is conjugate to g, and the conjugacy here is c. What is it? It's r minus k plus 1 minus epsilon. So this thing is yay smooth. Okay. So for bounded type where k is 2, it's enough to have C3. You have a smooth conjugacy. I mean, you make a Diffenton condition worse, you need smoother maps. Okay, very good. I'm not going to talk about this at all anymore. So because now I want to talk about this transformation as a dynamical system. I want to talk about R as a dynamical system. And here this gluing business really becomes a problem. It is difficult. I mean, I don't want to say it's impossible. Who knows? But it is difficult, and it has conceptually difficult to define an appropriate structure. Like, if you want to talk about this as an operator, you would like to talk about some Banach space structure in which this operator is, say, at least differentiable. So, and that becomes difficult in the context of these commuting nonlinear interval exchange transformations. I mean, I'm not going to go into the details, but you can imagine that this is not a natural object, right? Even in one dimension. So, fortunately, we can recover the situation when we go to analytic maps. So, if f is analytic, so if it's C omega, and I do the same exact thing. So this is 0, and this is FQN of 0. And I have this yellow interval, and I have a problem because I would like to glue a neighborhood of this point to a neighborhood of this point with the iterate FQN, but FQN is only analytic, right? So this is not going to give me an affine structure back. So the solution to this is the following. Since the map is analytic, you can extend this picture a little bit to the complex, right? So if I take, say, a straight segment here, not very tall because I don't know how far this extends, but if I take a straight segment here, then the image of this is, you know, is a segment, straightish kind of, going through this point. And now instead of gluing the neighborhoods of points, I could glue the neighborhoods of these. And if I also truncate this arbitrarily on the top, just taking a point, its image, a point, its image, and just gluing like this, then this becomes a Riemann surface. And it's a Riemann surface on the top of the topological type of a cylinder. Right? And now the Riemann surface magic takes over, because if this has topological type of the cylinder, then there is essentially a unique way to uniformize this to a cylinder. Right? So if I take this rectangle, let's give it a name. Let's call it, say, well, R for rectangle is bad because we already used R many times. Let's call it omega. Okay, so if I take this omega and I quotient, so I'm taking some epsilon neighborhood of this, and I'm quotienting by Z is equivalent to Fqn of Z. I'm going to get a Riemann surface. So this is a Riemann surface, which is like a cylinder, right? And now a cylinder like this doesn't have any non-linear self-automorphisms, right? All complex automorphisms of this are linear. They're all affine. In fact, if I normalize this at one point, if I say send 0 to 0, then there's only one of them, the identity. And now, so, okay, did you follow this? I mean, I glue this into a cylinder. I glue, uniformize. There's a non-trivial change of coordinates, probably very nonlinear one, which does this. But the upshot is that I recover the circle. Now, there's a canonical affine structure. Now, this is R mod Z again. And I have succeeded in gluing, and I have defined the renormalization in such a way that this is a well-defined map of the circle again. And that's great, because now there is a nice Banach space structure. I could just look on maps of a neighborhood of a circle, bounded analytic maps, blah, blah, blah. That's a Banach manifold, and this procedure gives me a Banach manifold again. So now we could talk about this as an operator. I mean, it's an analytic operator now, because I'm taking an iterate and then taking this change of coordinates. This change of coordinates depends analytically on the map, assuming all the other choices are made in the same way. And therefore, I got myself an analytic operator. So I could talk about it as a dynamical system on the space of maps. But before we do that, let me talk about rigidity results in analytic setting. The first rigidity result in the analytic setting, historically, in this context, is due to Arnold. The kind of the ultimate result is due to Yokos. Before I formulate Yokos' result, so the idea is the same. As you renormalize, I mean, how about I don't write this down again. I mean, if you renormalize, you converge to rotations exponentially fast. Assuming your rotation number is good, you're going to recover a rigidity result. So in the exact same mechanism is going to give you a conjugacy. How good should the rotation number be? So in this case, the condition on the rotation number was formulated by Bruno in the 70s, and these are known as Bruno numbers. And the Bruno condition, so maybe I call this class B. Bruno condition is the following: the log Qn plus 1 over Qn has to give you a convergence series. Okay? Now, this is much weaker, much weaker than a Diophantine condition. For a Diophantine rotation number, this is going to have a geometric bound. So this is going to converge like a geometric series. Okay, and then Yokos' theorem is the following. That if F is, well, if rho F is in B, so it's Bruno, and F is close enough, where enough depends on the rotation number, to affine, then F is analytically conjugate to the rotation, rigid rotation, just, you know, Z maps to Z plus rho of F mod the integers, rigid rotation by this angle. And of course, that means that if you have F and G that both satisfy this condition, the rotation numbers are the same, then they're analytically conjugate. So there's your analytic version of smooth rigidity. Okay? So now, but now we actually have an operator which is smooth, which is better than smooth. It's analytic. So we can actually talk about its properties as a dynamical system. And let me just say a few words about these properties. So this is a theorem that we proved recently with Natasha Goncharuk. And it says the following, that rotations are a hyperbolic set of this operator with one-dimensional unstable direction. And if you're puzzled about what all of this means, I'll draw you a picture. Okay, so we know that renormalizations will converge to rotations exponentially fast, right? So here, well, rotations are parameterized by one parameter, by the angle. So these are rotations by angle alpha. Okay, in this direction, in the alpha direction, my map is the Gauss map, which is very expanded. So the claim is that all other directions are contracted geometrically fast, and from the general theory of hyperbolic maps, we know that this means that if I take an irrational point here, yeah, so, okay, I have to say, I should have said Bruno rotations. Of course, I didn't. So I do need a nice condition on the rotation number. So if I take an irrational point here, which is in the Bruno class, there is going to be a stable manifold which passes through this. So this is my space of all analytic diffeos. This is a Banach manifold. This is just a line. This is a codimension one submanifold. And then here I have convergence like this, and then here, this is unstable. And this is true at every point. And in fact, what we also showed with Natasha, that these manifolds are the same as analytic conjugacy classes of maps. So this is the same as the analytic conjugacy class it's not very difficult to show that the inclusion that way, the inclusion the other way is non-trivial. This is a strong version of a theorem of Rissler. Running out of room. Who proved that analytic conjugacy classes are codimension one submanifolds in any finite dimensional slice around rotations. Now, don't worry, I'm watching the time. I'll be finishing shortly. Here's the thing. So far, I only talked about homeomorphisms. What about general analytic maps? Well, sorry, diffeomorphisms. So what about general analytic maps? So here I'm close to rotations. So these are obviously locally conformal diffeos. But if I start moving far, then critical points may appear, right? So the maps could stop. I mean, a homeomorphism of the circle, if it's in C omega, it will have finitely many critical points of a finite order, right? But it could have them nonetheless. So what will happen? So interestingly, historically, this study of hyperbolicity, it started with maps of the circle with critical points. And in fact, was a theorem of mine from a while ago. The generic case, so here is a critical circle maps. It's a in the appropriately defined space, it's a codimension one submanifold in which you have a single cubic critical point. Well, I mean single and cubic because this is the generic degeneracy. Anything else would give you a higher codimension. It has to be cubic, right? Because if the order is even, you will not have a homeomorphism anymore. And then here, there's a corresponding hyperbolic picture, except the invariant hyperbolic set is not rotations. Here, life is much harder. The maps don't become more linear when you renormalize. In fact, the nonlinearity persists because the maps will always have a critical point, so they cannot be linear. Nonetheless, there is an invariant set. It's better in some sense. So this is a Cantor set here. It's better in some sense because you don't need any condition on the rotation number, except the fact that it's irrational. So I'm going to connect these pictures. So in fact, another thing that we did with Natasha Goncharuk more recently, quite recently, is we connected these pictures. So it's known that if you impose a slightly more restrictive condition known as Herman condition on the rotation numbers, then these manifolds will reach all the way to here. Okay, so they become stable and unstable manifolds, separators. I mean, they connect the hyperbolic set here with the hyperbolic set here. And what we showed, I mean, then natural questions to ask. I mean, this is an analytic submanifold. The natural question to ask, how badly does it oscillate as it reaches here? I mean, what is the structure here? Right, so you could, the standard theory gives you smoothness in terms of the ratio of logs of the eigenvalues. So what we showed is that the expansion here, which is due to the hyperbolicity in this picture, is stronger for good rotation numbers than the expansion this way, which forces these to be smooth near the ends. So this was a long-standing conjecture. You can't quite resolve this without looking at this operator as a dynamical system. Of logs, ratio of logs. So for instance, for the golden mean, numerically, people were getting 2. And the ratio of logs is actually 2.05. That's just how it is. Okay, so I mean, for some specific values, people knew this numerically. I mean, for a large class of rotation numbers, you could get a general. So, okay. What happens if you go the other side of this hypersurface? Then these stop being homeomorphisms. I actually know the answer to this, but I'm not going to talk about that sort of work in progress. But just 2 words, since I mentioned things like Herman rings and so on. Another way you can extend this, I mean, hyperbolic dynamical systems are wonderful because the hyperbolicity persists under small perturbations. So you could extend this picture from 1-dimensional maps to 2-dimensional maps. The hard part actually lies only with extending the definition of renormalization to 2-dimensional maps. I mean, as soon as you've done it coherently, the rest is standard. I mean, follows from the general theory. In fact, so I extended this definition here on this side in such a way that this extension does not give any new unstable directions. So there are infinitely many more stable directions, but they're all stable, which correspond to extension to dissipative 2-dimensional maps. The attractor is the same, the hyperbolicity is the same. So for those in the know, this implies that Herman rings of analytic one-dimensional maps persist for small two-dimensional perturbations. So if you take, say, a rational map with the Herman ring, you construct an null-like map out of it, right? So then the Herman ring will persist. And what happens for critical maps? Again, some strange reason historically we did this first. So here we did this extension to two-dimensional maps with Denis Gaidashev. And we get, for two-dimensional analytic maps, we get there's another conjecture of Enrique Pujol's. We get these critical circles, so invariant circles on which rotation is not. So these correspond to maps who live in the stable manifolds, but in the critical slice, and these are not analytically conjugate to rotations, only smooth. I haven't talked about rigidity results here. Let me just throw some names. So we have a series. So for critical circle maps, I proved the corresponding rigidity result with Dima Khmelev. The corresponding result is a much weaker conjugacy. It's only C1 plus alpha at the critical point, but that's optimal. You cannot do better. On the bright side, this is true for all rotation numbers. Okay, and recently, with Igor Garbovitsky, we extended it for the general case of analytic homeomorphism. So for the degenerate cases as well. So for the situation when you have many critical points of various criticality. To complete the picture for homeomorphism, we also need a hyperbolicity picture for those. That would lead to a very complicated mess, right? Because you will have much higher codimension spaces and so on. And I'll be optimistic and I'll say we're almost there. Okay. Can I end with a little sermon? So okay, so here's it's a very niche joke. So there are some books which literally end with sermons. So for instance, there's a book by Leo Tolstoy, which is called Resurrection, which is I would say rather a trashy novel until the end, and then it ends with a 30-page sermon. So this is what I'm going to do. Here's a sermon. So it is very useful to look at renormalization as a dynamical system. So it's really extremely useful. The general philosophy is that if you can define it, then renormalization will be a compact operator, which means that it's essentially a finite dimensional system on the space of dynamical systems. Okay, so it's kind of magic. You start with an infinite dimensional space of dynamical systems, but assuming everything goes well, you are going to get again what is essentially finite dimensional. So for instance, here it's essentially two-dimensional. There are only two meaningful dimensions here, right? I mean, one, the rotation number, and the other one between critical and non-critical. If you add higher criticality, you'll have more dimensions, which correspond to break and other critical points, but only finitely many. Okay? But on the other hand, the dynamics of finite dimensional maps can be quite complicated, even if these maps are purely hyperbolic. And somehow in all of the examples until, well, maybe here, we only looked at the examples in which renormalization has only one unstable direction. So everything reduces to one-dimensional maps. Already for two-dimensional maps, you get rather interesting results. So even if these maps are hyperbolic, this is rather non-trivial. I mean, one could ask, in general, whether one can produce meaningful examples in which you have 3 dimensions, 10 dimensions, whether you could do it in an arbitrary dimension. How bad can the dynamics of renormalization be? That is quite interesting. I mean, it should have really interesting consequences for the underlying maps. Rigidity would fail in interesting ways, and so on and so forth. And so this is kind of the sermon. I'm going to leave you with this thought. I have, I don't know how to do this. I mean, I don't know how to cook up designer examples like this. I would be very happy to see a way to do it. And also, it would be very nice to find natural examples of dynamical systems in which this actually happens. Okay, full stop. Thank you for your attention.
Questions?
Yeah, when you edit this, please cut out the business about Leo Tolstoy and the trashy novel.
Yeah, okay, yeah, sure. I will try to remember it, but
Very quick
Sure.
question, because it's very interesting the way that you use the renormalization, getting some information about the rigidity. But I was wondering if the method of renormalization tells you also something about the statistical properties of the system, of the original systems, from the point of view of quantitative estimates, and from the point of view of the ergodicity, mixing, and
Sure.
this
Yeah.
kind of
Yeah.
stuff.
So the short answer is yes. I mean, so this goes into the same basket as rigidity, right? So you don't really need to study this as a dynamical system as such, but you need to look at whether renormalizations converge or live in a compact set and so on. And people have been using this under different names. For instance, people use names induced maps and so on, which is really rescaled first return maps. And this is, I would say, the mechanism by which you study such things as minimality, mixin, and so on. Yeah. So the answer is very much yes. Rigidity is just one application.
okay.
Like, I mean, even here, right? I mean, if I get C1 conjugacy to rigid rotations, that means that my unique, invariant blah 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 is absolute measure is absolutely continuous with respect to Lebesgue. So here is your right, here's your yeah. So this is precisely what I'm saying. So in this case, the same argument which I use to produce say smooth rigidity tells you that there is a unique, absolutely continuous invariant measure.
Doesn't tell you that it's going to be.
I mean, you have a smooth conjugacy
Yes,
to
absolutely.
rotation. So this is just a lift of Lebesgue measure by the conjugacy, pullback of
Yeah,
Lebesgue.
yeah. No, I was
Yeah.
thinking about more quantitative results, like the decay of correlations, and then you will relate.
Yeah. So yes, absolutely. You have to look at return times which correspond to renormalization and so on. Yes, but yes, absolutely, very much so.
Okay,
So in fact, if I may, just a quick thing. So if you think of all of the theory, so the theory in the linear case for this type of maps becomes interesting as soon as there's more than two intervals in the interval exchange. And then if you look
to ask this.
Huh?
I was about to ask about
Yeah.
this.
So and then obviously, if you look at the whole theory, I mean that this is all renormalization, right? So all the tools are renormalization.
Dimensional.
Right. I mean, it's not one dimensional.
This is one dimensional,
No,
but the renormalization is not.
That is correct. Yeah. But somehow, no, I see what you're saying, but somehow, and I know that there are people who work on nonlinear interval exchange transformations, but sometimes, yeah. So yes, I hear you.
It's a lot, Misha. Thank you. Okay.